Okay, let's look at the trend for electronegativity. And so this one here with electronegativity, you're going to find that it's the same as that the trend is the same for the most part as ionization energy. All right? So going up a group, and electronegativity, I should say, is the ability for an atom to attract an electron to itself. So as you go up a group, atoms can better attract electrons. So electronegativity increases going up a group, and it also increases as you go from left to right across the period. All right. There is one exception, is that the noble gases don't are not given an electronegativity value. They have a full valence shell, so they don't attract electrons to themselves. So they're not given an electronegativity. All right, now a couple things. The trend is the same as ionization energy, and what you're going to find if you watch that video or you've learned about it is that the reasons are pretty much the same. And so what I'm going to do is go to a kind of a broken down periodic table, or one that shows like a group trend and period trends, and we're going to discuss it from there. All right, so first of all, we're going to discuss the group trend. So we're going to be going down. Remember the trend, as you go up a group, atoms can better attract an electron to themselves. So we can use a simplified version of Coulomb's law again, and we can say that the force of attraction is equal to the charge, the positive charge, which is in the nucleus, which is based upon the protons in the nucleus. Basically, protons attract the electrons, times the charge of the negative charge, which will be the charge of the electron that it's trying to attract. We're going to divide that by the distance the electron is from the nucleus squared. And that will be the force. That's how much force of attraction, or that's how well they can attract. So now, if we look at lithium, let's just say that for some reason there was an electron here that it was trying to attract, and we compare that to potassium. All right? And we're going to try to think about, okay, which one's going to attract an electron better? Which one has a greater ability? Well, the first thing is that lithium, the electron that lithium would try to attract, is very close to the nucleus, versus potassium, that electron is very, very far away compared to lithium. Now, these models don't quite show exactly how it would be, but if you can look at it, you can get the idea. Basically, the further away something is from the nucleus, the harder it is to attract, or the less force of attraction there'll be. Kind of like magnets. Magnets work pretty good when they're close to things, but they don't work very well when they're far away. So you can think of it kind of the same, although it's an electrostatic attraction in atoms, not magnetic attraction. So anyway, the further away an electron is, the less electronegativity it has. So lithium would have a greater electronegativity because the electron would be closer to the nucleus. All right. Now the other thing you might say going down, well, hey, look, potassium has 19 protons. Wouldn't that attract better than 3? Well, that would be the case, except the shielding effect once again gets in the way. All the inner electrons block this atom, like potassium, from attracting an electron that's outside of the atom. And so, anyway, all these inner ones would shield the nucleus from attracting. Okay, so for the group trend, you're going to want to mention these two things when you talk about electronegativity. Okay, so basically, the closer the electron is, the greater the electronegativity. So I'm going to write it like this. The smaller the atom radius, the greater the electronegativity. Now, if you look up electronegativity values, I didn't spell that right. If you look them up, you'll see there are some exceptions, but in general, the smaller the radius, the greatest electronegativity. So also, in a group trend, another thing that you're going to want to mention is this factor right here, and you always mention this in group trends, is that the shielding effect decreases the effective nuclear charge. So when you write out on a test or something, when we ask you like which has the greater electronegativity, lithium or potassium, you would say lithium, and you would mention that lithium has a smaller radius, and the shielding effect kind of decreases the effective nuclear charge on potassium, and therefore lithium would be able to attract an electron better, so it has a higher electronegativity. Okay, so that's the group trend. Basically, the smaller the radius and the shielding effect are things that you're going to want to mention. Okay, now let's look at the period trend. So electronegativity increases this way going across the period. All right, so we can look at this simplified version of Coulomb's law to figure out what we would write down for the period trend. Okay, so once again, if you go across the period, you notice that the radius gets smaller. So in the period trend, you could also mention the radius. Okay, because see, if the distance is smaller, the force of attraction is greater. So if we compare lithium to nitrogen, and they're both trying to attract an electron that's outside of the atom, well, the electron for nitrogen would be a lot closer than the electron for lithium. So once again, with the period trend, the smaller the radius, the greater the electronegativity. I'm just going to abbreviate that. The greater the electronegativity. All right? Now, there's one other thing in a period trend that you always want to mention when you write about this. Look at lithium has 3 protons. And so you could substitute in a 3 there. So, we could put in, for lithium, we could put in like 3 protons, 1 electron that we're trying to attract. Divided by the distance, we could maybe just make up a number, but whatever units this would be. So we're going to say there's like 4 units for lithium. And if we compare that to nitrogen, okay, we could say, well, nitrogen, the force of attraction would be equal to 7 protons, okay, times the 1 electron that we're trying to attract, divided by the distance. If I kind of use the same measuring value, it's kind of hard to measure, but I'm just kind of making these values up. I don't know what they would actually be, but we'll just say 2 units. Basically, what I'm trying to show is that nitrogen has a much smaller radius than lithium. So if you look, all right, if you're comparing, nitrogen would have a much greater electronegativity because it has a smaller radius when compared to lithium, and it has a greater effective nuclear charge. And the reason is because basically, as you go across, nitrogen has more protons in the nucleus. Okay, and the reason that it would have is more protons in the nucleus. All right, so electronegativity increases going across a period because as you go across, the radius gets smaller and the nucleus gets more powerful because there's more protons in the nucleus, so they have a greater effective nuclear charge to attract that electron. Okay, going across the period, shielding is never ever a factor because shielding is constant in period trends. All right, so going across the period, shielding is never a factor. Shielding is always a factor in group trends. Okay, but the main thing to look at is the smaller the radius, the greater the electronegativity. That's why it increases going up, and that's why it increases going to the right. Also, the shielding effect in group trends decreases the effective nuclear charge. All right, but going across, shielding is constant. The protons increase. That makes it more able to attract an electron, and so that's why the electronegativity increases going across. Okay, that's it on that video.